Hi friends, welcome back to a new session. See, in the last session, we started effect of non-linearity and saturation of magnetic core on the operation of transformer. There we concluded for having sinusoidal flux EMF waveforms, shape of I mu should be peaky, or if we don't want harmonics in flux EMF waveforms, harmonic should present in I mu waveform. That is the conclusion we got. So or I can say, if we want to make flux EMF waveforms free from third harmonic should be there in I mu waveform. That is the last I just made conclusion. And one more thing I also told. That means indirectly there should be third harmonic current should be there in I mu waveform means what? There should be paths for your third harmonic currents from phase to phase or from line to line. That is the conclusion I just made. Okay, please try to see our last session conclusion. Now, so let us see. In the last session, I told there should be paths for third harmonic currents between phase to phase or line to line. Then only shape of a flux EMF waveforms becomes sinusoidal. Shape of I mu becomes a peak. So before deciding whether path is there or not for third harmonic currents, let us see whether path is there or not for fundamental currents, for negative sequence currents, for positive sequence currents. Then we'll see about your third harmonic currents also. Okay. So here you have to understand small thing here. So if you take in a three-phase system, please try to let me tell you an important point. Any component of current, I'm saying any component of current, maybe fundamental current or fifth harmonic, seventh harmonic, or third harmonic, any harmonic, any component of current will flow from phase to phase, or line to line, if it satisfies fundamental property. See here, I told you in last session, we have to decide whether path is there or not for third harmonic currents. Before deciding for third harmonic, I am just generalizing this statement. Any component of current, maybe fundamental current, maybe fifth harmonic, maybe seventh harmonic, maybe third harmonic, any component of current will flow from phase to phase or line to line if it satisfies fundamental property. Example, generally if you take this one as fundamental current, I can take this one as a fundamental current. And generally we are having harmonics, right? We are having a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and so on. These are harmonics. Now I already told you one point. I mean, if waveform is symmetrical about x-axis, symmetrical about x-axis, if waveform is symmetrical about x-axis, even harmonics will cancel with each other. Even harmonics will cancel with each other. Suppose if waveform is symmetrical about x-axis, if even harmonics will cancel with each other, That means I can say that let me cancel even harmonics 2, 4, 6, 8, 10, 12, 14, 16 and so on. And let me take remaining harmonics. It is a fundamental, okay. And the remaining harmonics you are having what? The 3, 5, 7, 9, 11, 13, 15, 17 and so on. These harmonics can be called as what? Odd harmonics. What? Odd harmonics. Odd harmonics. Odd harmonics. Okay. Right. See, these odd harmonics are divided into two groups. Odd harmonics divided into two groups. Why I just divided two groups means because these two groups behave in a different way. I'll tell you in what way they are behaving differently. I'll tell you that. Since they are behaving differently, I can say that I just divide odd harmonics into two groups. Group 1, I can say that n equal to 3m plus or minus 1, where m is even number. That means what you'll be getting? 3 2s are 6 plus 1 7, 3 2s are 6 minus 1 5, 3 4s are 12 plus 1 13, 3 4s are 12 minus 1 11, 11, 13, so on. And second group nothing but n equal to 3m, where m is odd, means 3 1s are, okay, 3 3s are, 3 5s are, and so on. These are the harmonics. Okay, why I just divided odd harmonics into two groups, I'll tell you that. Before that, let me take first fundamental. Let me take first fundamental currents. Fundamental currents. Okay. Nothing but I'll take IA1, IB1 and IC1. These are the fundamental currents, right? In a three-phase system, IA1, IB1, IC1 are the fundamental currents. So I'll take reference IA1 is reference. After 120 degrees you'll get IB1. After 240 degrees you are getting IC1. So what is the phase sequence here? ABC is the phase sequence. So let me write once again. This is what IA1. This is what IB1, IC1. I have taken IA1 as reference. After how many degrees you are getting this IB1? 120 degrees. After how many degrees you are getting IC1? 240 degrees. Compared with your reference I am saying. Okay, 0, 120, 240. Now, I told you here, any component of current will flow from phase to phase or line to line if it satisfies fundamental property. Fundamental property means, just listen. Fundamental property means what? Fundamental property means, I can say very simple. Fundamental property nothing but phase displacement angle between those components of current should be equal to 120 degrees electrical or vector sum of IA, IB, IC components should be equal to 0. This is only fundamental property. Now tell me, so just please try to remember this fundamental property. I can say basic property. So phase displacement angle should be equal to 120 electrical or vector sum should be equal to 0. Then only that particular component of current will flow from phase to phase or line to line. So here, what is the phase displacement angle between these three vectors? 120 degrees electrical. Okay. Or I can say, what is the vector sum of IA1, IB1 and IC1? How much? 0. That means fundamental currents, if you see clearly, they are displaced by 120 electrical, their vector sum equals to 0. Therefore, fundamental currents satisfies fundamental property. I will write simply fundamental property. I can write it as F dash P. Fp satisfies fundamental property. Therefore, these currents can flow these currents can flow from phase to phase, or line to line, from phase to phase or line to line. Example, if you take a star connection, if you take star connection like this, since it is satisfied fundamental property, they will be having flow from phase to phase or line to line. Example, A phase, B phase, C phase, if you take, okay, if you take example IA1 current, I'm just taking IA1 current, it will flow from A to B, phase to phase it will flow. It will be similar, it will flow from A phase to C phase it will flow. If you take IB1 also, it will flow from B to A and B to C. So flow is there because it is satisfying fundamental property. This is star connection. Suppose if you take delta, connection also, so since these currents satisfy fundamental property, they will be having flow from phase to phase or line to line. So I can say A phase, B phase, C phase. If we take IA1 here, yes, it will flow from A phase to B phase like this, A to B, A to C. Similarly, if you take IB1 also will flow from B to A, B to C. So here I just concluded that fundamental current satisfies fundamental property. These currents will flow from phase to phase or line to line. So like that I'll go for next, this is fundamental, I just complete, right? Next we'll go for n equal 3m plus or minus 1. Okay, there I'll decide whether path is there or not for n equal 3m plus or minus 1 order harmonic currents. Next I'll go for n equal 3m. There we'll discuss about the third harmonic. Okay, so this is our main topic here. Whether path is there or not for third harmonic, that we have to decide. Okay, so before that we have to explain fundamental, as I explained here. Next we have to explain n equal 3m plus or minus 1. Next I'll go to n equal to 3m where m is odd. So here fundamental current phase sequence how much? ABC is a phase sequence. Okay, so here conclusion you can say that fundamental current satisfies fundamental property. These currents can flow from phase to phase or line to line. Okay, please note down. Then after that I'll go for n equal to 3m plus or minus 1 order harmonics. Right. Next we'll think about n equal to 3m plus or minus 1. See, let us see here. Let us think about n equal to 3m plus or minus 1. I already told you that odd harmonics are divided into two groups. N equal to 3m plus or minus 1 is the one group. N equal to 3m is the another group. I'm just taking here n equal to 3m plus or minus 1, where m is what? Even number. In that one second I'm just taking n equal to 3m plus 1 I'll take first, where m is even. Next we'll go for n equal to 3m minus 1. Okay, first tell me n equal to 3m plus 1, where is m is even number. 3 2s are 6 plus 1, 7. 3 4s are 12 plus 1, 13 plus and so on. Here example, please take a 7th harmonic and let me generalize the conclusions which are valid for 7th harmonic will be valid to n equal to 3m plus 1, right? 7th harmonic. You tell me, I am asking what is the angle between IA7, IB7 and IC7? Generally, you know, IA1, IB1, IC1, what is the angle between this IA1, IB1, IC1? 0, 120, 240, right? 0, 120, 240. Now I am asking for 7th harmonic. Just multiply simply with 7, that's it. Into 7, into 7, into 7. You'll get here 0. Here you'll get 840. 840 should be, I mean, from that 840, 360 multiples has to be subtracted. Example, 840 minus 360 multiples. If I subtract 720, once again you will get 120. Here also you'll get whatever the value you are getting minus 360 multiples. You just subtract. You'll get once again 240 only. So what I mean 0, 120, 240 means what? If I take IA7 is as reference here, IA7 reference. After 120 who is coming? IB7. So this is what I can say IB7. After 240 what is who is, I mean you are getting I7. Now what is the phase sequence here? A, next B, next C. A, B, C is the phase sequence. Now let me ask a simple question. So just like fundamental you told, phase displacement angle between these components equal to 120 you wrote. And their vector sum equals to 0 you told. Already just very simple thing. If 3 vectors are displaced by 120, their vector sum becomes 0. Now here tell me what is the phase displacement angle I am asking you. Same. So see 0, 1 to 240. Here also I can say that 120 degrees electrical only. Or I can say IA7 plus IB7 plus IC7 should be equal to how much? 0. Therefore, 7th harmonic, or I can say n equal to 3m plus 1 harmonics. Therefore, n equal to 3m plus 1, where m is even, order harmonics, satisfies fundamental property, comma, they can flow from face to face or line to line, just like fundamental currents. How fundamentals are flowing from A phase to B phase, A to C, B to A, B to C, C to A, C to B. Here if you take IA7, it will flow from A to B, A to C. And if you take once again IB7, it will flow from B to A, B to C, like that. Okay, right. Now here one thing you have to understand. So ultimate, what is the conclusion? N equal to 3m plus or minus 1. If I take n equal to 3m plus 1, these n equal to 3m plus 1 harmonics can be called as positive sequence harmonic currents. Why we are calling it as positive sequence harmonic currents means very simple. What is the phase sequence of fundamental? ABC is the phase sequence. What is the phase sequence of n equal to 3m plus 1, or I can say 7th harmonic? ABC only. Is it clear? Therefore, n equal to 3m plus 1 odd harmonics can also be called as positive sequence harmonic currents. What is the reason? Why? What is the reason? Why you are calling it as a positive sequence harmonic currents? Since phase sequence is same as that of what? Fundamental. That's the reason why we can call the n equal to 3m plus 1 order harmonics as positive sequence harmonic currents. So now please let me conclude up to this. Fundamental current satisfies fundamental property. See, fundamental currents satisfies fundamental property. So these currents can flow from phase to phase or line to line. Similarly, n equal to 3m plus 1 order harmonic currents satisfies fundamental property. They can flow from phase to phase or line to line, just like fundamental currents. Okay, first note down this, then I'll go for I just completed only n equal to 3m plus 1. After that n equal to 3m minus 1, one more is there. Let me calculate n equal to 3m minus 1. Then I'll go for n equal to 3m, where you'll get a third harmonic. Okay, where you'll get third harmonic. Our main topic is the third harmonic. Before explaining third harmonic, I'm explaining n equal to 3m plus 1, n equal to 3m minus 1. Then I'll come to third harmonic. Okay, please note on this. Right. Now observe guys clearly. We completed fundamental currents, and in n equal to 3m plus or minus 1, we complete n equal to 3m plus 1. Please go for n equal to 3m minus 1, n equal to 3m minus 1, where m is even number. So 3 2s are 6 minus 1. Okay, 5. 3 4s are 12 minus 1, 11, and so on. Okay. Here example, please take fifth harmonic, and whatever the conclusion is valid for fifth harmonic, it just made it valid for n equal to 3m minus 1 also. Now see here, this is what IA5, IB5, IC5. I'm asking angle between these IA5, IB5, IC5. You know, generally it is 0, 120 and 240. I'm asking for fifth harmonic. So generally fundamental condition is 0, 1, 240. If you multiply with into 5, into 5, into 5, you'll get 0. Whatever the value you'll get, you just subtract that value. I mean, it's just whatever the value you're getting, from that please subtract 360 multiples. You'll get here 240. Here you'll get once again 120. You'll get here 120. Okay. That means what? If I take IA 5 here, after 120 who is coming? IC5 is coming. Next, IB5 is coming. What is the phase sequence here? ACB is the phase sequence. ACB is the phase sequence. ACB is the phase sequence. Now tell me, here what is the phase displacement angle between these three currents? Say 120 degrees only. 120 degrees only. Next, what is the vector sum of IA5, IB5 and IC5 is equal to how much? They are displaced by 120, so vector sum becomes 0, 0. So whatever the statement here I wrote, n equal to 3m plus 1, where m is even, order, harmonic, satisfies fundamental property. Same statement I can write for n equal to 3m minus 1 also. Okay, so let me write that statement here. N equal to 3m minus 1, where m is even, order, harmonics, satisfies what? Satisfies fundamental property. They can flow from phase to phase, or line to line. You may get one doubt. See, n equal to 3m plus 1 is also satisfying fundamental property. They are flowing from phase to phase. Like example, fundamental currents, they are flowing from IA1. Example, if you take, it is flowing from A to B, A to C. If you here also for delta, if you take IA1, it is flowing from A to B, A to C. Similarly, IA7, IB7 also, IA7 here, IB7 here, I7 here. IA7 in delta, IB7 in delta, I7 in delta will flow from phase to phase or line to line. Similarly, n equal 3m minus 1 order harmonics also satisfies fundamental property. And those currents also can flow from phase to phase or line to line. But only difference is, difference between this fifth harmonic and seventh harmonic. Difference between this fifth harmonic, okay, and I can say that fundamental and seventh harmonic is same only, because phase equals ABC, here also ABC, it is okay. That's why we are calling n equals 3m plus 1 odd harmonics as positive sequence harmonics. Here phase sequence ABC. What is the phase sequence of fundamental? ABC. Therefore, that's the reason why we are calling n equal to 3m minus 1 odd harmonics as a negative sequence harmonic currents. Negative sequence harmonic currents. Why? Since phase sequence is opposite to the top, or I can say opposite from the top, fundamental, or I can say positive sequence currents. Here also phase displacement angle is 120, vector sum becomes 0. Here also they have satisfied fundamental property, so it can flow from phase to phase or line to line. See, n equal 3m minus 1, where m even odd harmonics satisfies fundamental property. They can flow from phase to phase or line to line. What is the difference? So there mean if example, if you take seventh harmonics, if they are flowing from source to load, these negative sequence currents will flow from load to source. Path will be there, but direction will be different to that of your seventh harmonic currents. Okay, so just remember, n equal 3m plus 1 means positive sequence harmonic currents, n equal 3m minus 1 means negative sequence harmonic currents. Is it clear? Now, after this, up to now we completed fundamental, n equal 3m plus 1, n equal 3m minus 1, where m is even. Now I'll go for n equal 3m, where m is odd. Okay, where m is odd. This is only our important topic. Okay. Yes. Let me go for n equal to 3m. N equal to 3m, where m is what? Odd. Where m is odd. Where m is odd. So m is odd means what? 3 1s are, 3 3s are, 3 5s are, okay, 3 7s are, and so on. So see guys, n equal to 3m harmonics can also be called as, these harmonics can also be called as triplet harmonic currents. Triplet harmonic currents. And here, for understanding your n equal to 3m order, let me take example third harmonic. I'll take. Now tell me, IA3, IB3, IC3. Generally fundamental current displaced by 0, 120, 240. I'm asking for third harmonics. So what you have to do? Into 3. So you'll get here 0, 0, 0. 0, 0, 0. So this is IA3, IB3, IC3. IA3, IB3, IC3. See, what is the phase displacement angle between these two vectors? 0. Phase displacement angle is equal to how much? 0 degrees. That's why these harmonics can also be called as, cofacial currents. What is the reason? Since they are parallel vectors. Cofacial currents. Okay, cofacial currents. And tell me, here, since they are displaced 0 degrees electrical, we should not say, vector sum, but we should say arithmetic sum. Here, IA3 plus IB3 plus IC3, if they are displaced 120, that is equal to 0. But here, that distance by 0 degrees. Therefore, I can say that is not equal to 0. From these two statements, tell me n equal to 3m, or I can say third harmonic currents satisfies the fundamental property or does not satisfy fundamental property. See, fundamental property means what? Phase displacement angle should be equals to 120. Vector sum should be equals to 0. But here phase displacement angle is 0 and the sum is not equal to 0. So third harmonic currents satisfies or does not satisfy? I can say does not satisfy. Third harmonic currents do not satisfy fundamental property. Therefore, these currents cannot flow from phase to phase or line to line, Okay, please note down. Right. Here, please note down one more name is there for this n equal to same order, cofacial currents, triplet harmonic currents, or I can say zero sequence currents. Okay. Now, yes, see guys. Please try to refer a previous session. There I told you, if you want flux waveform sinusoidal or EMF sinusoidal, I told you IME is what? Non-sinusoidal. Please try to refer previous session. Or what is the other name I told? PK waveform. Or I can say, if I say fluxicum EMF waveforms, if we don't want third harmonic, here and here, in IME waveform, third harmonic should be there. That is our conclusion in previous session. There should be path for third harmonic currents. That means the third harmonic currents has to flow from phase to phase or line to line. Then only IME waveform becomes peaky, flux becomes sinusoidal, EMF becomes sinusoidal. Suppose if you are not able to provide path for third harmonic currents, IME becomes sinusoidal, flux becomes non-sinusoidal, EMF becomes non-sinusoidal. Now that's why we started our session whether we are explaining a path is there or not for third harmonic currents, and we conclude here fundamental third harmonic currents cannot flow from phase to phase or line to line. Why? Because these currents do not satisfy fundamental property. Then how can you provide a path for this third harmonic currents? Okay, Anyway, you have to provide a path for harmonic currents. Otherwise, your shape of flux coming EMF waveforms becomes here harmonics. If is not there in the IMU waveform, harmonics will come in a flux coming EMF waveforms. Your flux coming EMF waveforms becomes a non-sinusoidal. So here I need to write one statement. I can write note. Though third harmonic currents do not satisfy fundamental property. Though harmonic currents do not satisfy fundamental property, okay, still path can be provided. Between face to face, or line to line, if there is closure path, between I can say phases, Are you getting my question? Though thermal currents do not satisfy fundamental property, still path can be provided between phase to phase or line to line if there is closure path between phases, which is possible in delta connection, because in delta connection closed path is there between phase to phase, A phase, B phase, C phase, closed path will be there. Therefore, which is possible in delta connection, not in star connection, okay, not in star connection, okay. Please note on that. And see, after this, in our next session, we'll discuss how can we provide path for harmonic currents in a delta connection. And I am saying here it is not possible in star connection. So is there a remedy for the path of harmonic currents in star connection also? Those things we'll see in next session. Okay, please note on this.